Okay, it's a great pleasure to be here to celebrate Guy's birthday and achievements. So I'm gonna try to show you some of his achievements and try to tell you a little story about T of B theorems, maybe a big one, I don't know. It's not me to say. Okay, so how does it work? Okay, so any story has a beginning. So the beginning of this story today is this theorem by Ralph Koifman, and McIntosh and Meyer. So celebrated boundedness of the Cauchy integral operator on the Lipschitz graph. So the operator is a formula given there, and okay, it was a big achievement, of course. So I'm skipping a number of steps before the proof of this theorem, a number of contributions. I should quote Calderon, of course. Okay, that was one of the landmarks of the 80s, 82, in harmonic analysis. And the proof, I will come back to that, was simultaneous to the proof of another problem, the Kato problem in one dimension, with actually a similar technique. And the technique was the kind of multilinear analysis that Rafi and Yves were developing at the time, and also that McIntosh was looking at from a different perspective, more operator theory point of view, and merging these ideas, the three of them were able to achieve this result. And it was actually the beginning of a big venture for singular integrals, of course. 2 years later, there was this theorem of David and Journé, so Guy David here. Okay. So they proved the T of 1 theorem, which is a criterion for L2 boundedness of singular integral operators. So I'm not going to recall what a singular integral operator is. Let's say there's a formula with a kernel, and the kernel has size and regularity estimates. I guess that most of everybody here has seen that. Okay, so, but the size and regularity estimate are the order of not integrable on the diagonal and infinity, which makes the kernel representation singular somehow. And okay, so the criterion most of you know is that the operator is bounded if and only if quantities called T of 1, T star of 1, are in BMO, and T satisfies the weak boundedness property, which is some sort of control on the diagonal, which is not contained in the hypothesis of on the operator, and it's neither in the constraints that T of 1, T star of 1 are in BMO. Okay, and T of 1, T star of 1, you can compute them. Suppose that you truncate the operator in some sort, so it becomes an integrable kernel, and then you can compute T of 1, T star of 1 like you would do with an integral representation. And otherwise, if you don't have truncation, you define these objects by a limiting process. Okay, so, and now I put these two results on the board just to indicate that, okay, now there's this criterion proved after that theorem. Does the criterion apply? And of course, you can compute C of 1 if you want, and if you do a change of variable, you use a little bit of holomorphic function theory, like the residue theorem, then you can show that C of 1 is equal to 0. But the problem is that since you have a Lipschitz curve, you have used all the regularity of z in the derivative here, z prime, which means that this kernel, which is a combination of this thing, is no longer regular in the y variable. So you cannot apply, so it's not written like this, it's not a singular integral operator. So the idea that came next, it's here. Yes. Okay, I put the formula again. So you have C of 1, I told you, equal to 0. But you may factorize C as a product of two things. One is a singular integral operator with kernel 1 over z of x minus z of y. And the second one is a multiplication by the function z prime. Okay? And now if you forget about, if you look at t, then you if you apply z prime to t, that's C of 1, so that's 0 in BMO again. Okay, but the problem is z prime is not 1, of course. It's a bounded function, but which has some non-degeneracy. Recall that that z was x plus I phi of x. So z prime is 1 plus I phi of x prime of x. Okay, so the real part is 1, so it's bounded below by 1, of course. Okay, and so that gave the idea to Yves Meyer and Alan McIntosh and Yves Meyer to try to generalize the T of 1 theorem, and then this is what they obtained. It's not written like this in the short note that they wrote, but it's roughly what it says. It says that if you have a singular integral operator, and if you have a function b that plays the role of z prime, so it's bounded and accretive in this sense, then the L2 boundedness follows from these two computation tb and t star of b is equal to 0 star is just a real transpose to avoid complex conjugation. And that t of mb, t times mb is weakly bounded. So again, this is this control on the diagonal for this operator, and then the fact that you have some cancellation properties encoded by these two things. There are too many zeros here. Okay, one is enough. Okay, and the proof was in fact a consequence of an interpolation result that Alan McIntosh, I guess, knew even before the proof of the Kato problem, and this interpolation result is a consequence of the proof of the Kato conjecture. Once you have the Kato conjecture proved, you have an interpolation result at your hand, and then you can use it. So, and the proof was kind of course, indirect, but still it applies to C above. So that gives another proof of the first theorem. But of course, that's not very satisfactory, because you're using the same kind of tools, and then you're proving another criterion using the same kind of tools. Then so you're proving something new, but it's hidden is something that's not new. So you need for another proof. And this other proof is the T of B theorem of David, Journé and Semmes in 85. Okay, so I gave the assumption of this theorem just to compare with the T of 1 theorem and to compare with the previous one. So the criterion is that you have a singular integral operator and you have functions b1 and b2 playing the roles of the function b before. Just paracritic, I will say what it's here, so I will describe. But the L2 boundedness is again an if and only if condition. Now it's an if and if condition that you should have T of B1 and T star of B2 in BMO, and some kind of weak boundedness property for these product operators. Let me say that the weak boundedness property, it has lots of different ways of being expressed. So you could have only T MB1 or MB2 T MB1. So they all give statements. So you can pick your most favorite one here. And the paracutivity is it's a generalization of the accretivity in the sense that you don't only have the real part of B bounded below. You have some kind of integral of B mean value of B bounded below. But if you look at a given cube, that's your scale, you don't expect that on that cube you have the mean value bounded below, but you have that mean value bounded below on some subcube of P that has comparable size. And again, there are some equivalent ways of expressing the same condition. Okay. Okay, and the proof was at the beginning. The proof was very demanding, in fact, because to prove this theorem, you have to construct some kind of Littlewood-Paley decomposition that is adapted to the kind of analysis you want to do for the operator T. So it's a little decomposition, but it's compatible with multiplication by B1 and B2. So it was really involved. Let me mention that a space of homogeneous type, maybe everybody knows here, it means doubling measure. Okay, so metric space with doubling measure, or quasi-metric space if you want. Extra assumptions, well, technical assumption when you look at the paper is that the space has infinite mass, no atoms, and then there's a little condition, the annular decay condition, saying that if you look at a ball and if you look at an annuli inside that ball, the relative mass is small if the relative distance here is small, okay, in a quantitative way. So this is what the argument gives it, but in fact, 30 years after, you can just be convinced that these assumptions are not needed anymore. You have other proofs that eliminate this thing. Okay, so but this theorem was very inspiring for many directions as well. So the goal of my talk is to try to show you some directions that were taken after these theorems and what kind of result you can look at. Okay, so let me come back. So I said it's a global TOB theorem. Global means that in fact there is one function, well, there's two, but globally there's one function B1 and the other one for T star B2. So it's called a global TOB theorem because later we will have local TOB theorems where B will be allowed to vary depending on cubes. Okay, so maybe the next very important paper on global TOB theorems for singular integral is this paper by Nazarov-Terrell-Volberg. There are two of them, in fact, but this one is about global statement, where they prove the TOB theorem on a space of non-homogeneous type, which is like Rn equipped with a measure that's not doubling, but that's upper doubling in terminology of Heitonen, which means that the measure of the ball is controlled by a power of the radius. Okay, and it was a big achievement because when you don't have the doubling property, lots of estimates are very difficult to maintain. And in fact, in this paper, well, maybe I'm wrong. I'm talking under the control of Sasha here, but I think this is the first paper where the random dyadic structure was implemented for singular integrals. And also a little improvement in the statement is very low to replace L infinity condition on the B's by BMO type conditions. Okay, this is what the proof would give. So it was a very important step in this direction. Another direction is this little paper by Semmes in 1990, where he looked not at singular integral but square functions. So everybody knows in harmonic analysis, square functions come into the game very often. But in fact, there are some kind of simple object sometimes to look at because you already encoded one part of constellation when you write theta t in a norm. Well, when you write things like this, you already you're looking at one-sided constellation and not the other side. So what's theta t? Theta t is like kind of a smoothing operator, like a convolution. So it has integrable decay. It lives at scale t, and it has some smoothness only on the x variable. So you imagine the kind of smoothness you have from a convolution operator, but only in the x variable. So it's not a convolution, of course. And then you have some kind of convolution on the other variable. When you integrate theta t of b, you find 0. So just to fix ideas, theta t of b is just an integral that you compute from a kernel here. Okay. Okay, so the assumption on k allow you to define this integral in a simple way. And then you see that you don't need to use any Lie regularity in the kernel just to make sense of this. And then you suppose that it's 0, okay? And the assumption you take is the same as the David-Journé theorem. You assume that B is per-accretive. Okay, and under these three conditions, so Semmes is able to prove this inequality. And the proof that he produces is a proof that's very elegant. The idea is to show that this quantity is a Carlson measure. So you replace b by 1. So here you replace b by 1. So you just want to integrate the kernel in the y variable. And then it gives you a function of x and t, and you want this to be a Carlson measure on the upper space. And once you have this, you may apply an earlier result of Chris and Journé, which says that whenever you have this kind of operator, this kind of condition, then you have this estimate. Okay, and the idea of this is to use a reduction that was already used many times by Kaufmann and Meyer. Actually, they had another proof of the T of 1 theorem, which used these kind of ideas. I call it the principal approximation to apply Carlson's theorem. So just the idea is that you have some kind of approximation of your operator theta t, which is in the form of a multiplication by some function. So maybe times a smoothing operator like a true convolution or true averaging operator times PD of f of x. Okay, and this kind of object always have the square function estimates, so therefore you're reduced to looking at this kind of expression, and you are in the realm of applying Carlson's theorem. Okay, so that was a nice paper, which I looked at many, many times. Another really important paper in the area is an achievement by Michael Christ, who is the first to introduce this notion of local T of B theorem. So local T of B theorem means that the function b, b1 or b2 vary with the ball on which we want to look at things. So they depend, they're indexed by balls. Okay, and L infinity testing condition means that if you look at the statement, we have here boundedness and well, some kind of L infinity condition. So again, if you take your favorite singular integral operators, if there is a pseudo-accretive system of test functions, well, actually two of them, because there is 1 and 2, indexed by balls, such that when you apply t to b1b, it gives you a bounded function uniformly over the balls, and the same thing for t star of b2 of b. Then the conclusion is that t is bounded on L2. So pseudo-accretive system means that each of these functions is bounded and it's uniform with respect to the ball, and then this is notation for the average of this function on that ball is equal to 1 for all balls. So of course you can normalize b1 and b2 so that this is true. If it's bounded below, if it's a complex number bounded below, you can normalize. Things are in the complex fields, for example. Okay. But let me mention you can play with games with things that lives in the matrix setting or in Clifford algebra settings and so on. The space here on which you want to do the analysis, a space of homogeneous type. Michael Christ eliminates atoms. He doesn't want atom in his decomposition. Again, this is something that can be eliminated by now. But this is what he does. So how does he prove this? Well, this is first the paper where he introduces this system of diagonal cubes on spaces of homogeneous type that we will to be very important. And he used that to construct from the accretive systems b1b and b2b para-accretive functions. So you will create a function b1, you will create a function b2, both being para-accretive functions. They are adapted to t, in the sense that t of b1 will be in BMO, t star of b2 will be in BMO, and then he applies the David-Journé criterion. Well, again, a small gap at that time is that he has less, the David-Journé are more constrained at the time, but again, by now it's irrelevant. So it's a true deduction. And the motivation for doing this in his paper was to apply this to analytic capacity. So it was already a big achievement, but it was not enough to do that on spaces of homogeneous type. It needed to be done on spaces of non-homogeneous type. And let me mention 3 results in this direction. So big contributions. One of them by Guy, when he proves the Vitushkin conjecture. This is the title of the article. What he needed to prove, in fact, is the version of Christ's theorem on spaces of non-homogeneous type. And this is what he did, and it was not an easy task. A simpler proof was given by Nazarev, and Vauber, or this T of B theorem was given there. And the simplicity came from the fact that we use random dyadic grids. So what's the point of random dyadic grids in this story is that when you compute, well, some coefficients of T on, say, adapted R basis, for example, there are two easy things. The diagonal terms are usually easy because they're controlled by the weak boundness property that are here or there. The faraway terms, when the non-diagonal terms, you have the faraway terms, usually the tails are very easy to handle. The big problem is when you have two cubes that are very close to one another and at different scales. And the randomness allows you to say that most of the time, the coefficient, the size of the coefficient that you get is small. And you use this kind of probabilistic argument. And then, of course, the important achievement of Tolsa is to be quoted here, where, is the date correct? Yeah, okay. I wasn't sure. So when he proved the Panel-based conjecture on analytic capacity, so of course using in his arguments a local T of B theorems above. Okay, so that was one important direction where local T of B theorems were used. Another direction is towards the Kato square root problem. And I have to say that for me it was the influence of joining, oops, what did I do? Okay, joining two papers, so the Christ and Semmes paper. So because if you want to look at Kato square root problem, so Kato square root problem is to try to prove this inequality when you have an elliptic operator L given in divergence form. The coefficients A, so it's a matrix, bounded, measurable, and could be complex. And then you have some kind of ellipticity given in terms of the accretivity of the matrix. So basically the real part of A dot Xi, A applied to Xi dot Xi, Xi is a vector, is bounded below by a multiple of the length of Xi squared. Okay, so so Kato's conjecture was motivated by applications to hyperbolic equations. And it has more applications, of course. And why complex coefficients? Just to recall, complex. Once you have this estimate for complex coefficient, then you can use a complex function theory to say that if you perturb L, if you perturb the coefficient by an analytic parameter, then this estimate is stable in some sense. So this estimate is stable in the perturbations. So this is why you need complex, because then you use a little bit of complex function theory. It wouldn't do for real coefficient, for example. If you just had this inequality for real coefficient, the stability would not be granted. And let me mention that if you have A is self-adjoint, for example, A is equal to A star, this inequality, this comparison is straightforward by spectral theory. So there's nothing to prove. So the difficulty is when you're not self-adjoint here. And in fact, to prove this, there's a number of reductions, but to prove this inequality, it suffices to prove a square function estimate. So of course, the spirit of Semmes' paper is there. You have to prove some kind of things, where you have an operator which I call theta t before, but of course it's much less regular than the theta t that Semmes was considering. You don't have all the estimates you need for the kernel. And then it's, yes, so therefore you cannot apply directly this strategy. And in fact, I never saw a way of applying this, a global T of B theorem like Semmes did. But things are nice if you look at this kind of estimate, do this kind of reduction, you can. And then you end up with trying to prove some Carlson measure estimate of some coefficient. And in fact, so therefore things are reduced to local things. And so therefore you don't need a B that is a global function to test some constellation. You can have a families of B's that test your constellation. So in fact, what we proved with Philippe Chamichon in 1998 is that the Kato conjecture follows from a local T of B theorem. But again, if you look at this, you want L2 estimates, and basically, if you look at the proof, L infinity testing condition won't be enough for you because you don't have the good kind of estimate on the kernel. What you really want is L2 testing conditions. So in other words, you'll have to replace L infinity bound by L2 bounds rescaled in a proper way. I will come back to this later. But okay, so once this thing was understood, then the goal was to check whether this local criterion could be proved or not. And in fact, it is true. So it came in 2002 in a series of papers. So there are like 5 or 6 papers. So it was too long to write, but the people involved are here. Steve Hoffman, Michael Lacey, John Lewis, McIntosh, Philip Chamichan, and myself. And we proved in the end is that the square function estimate that I wrote just before is true. And therefore the Kato conjecture is true. I have a little anecdote. Since I'm here, it's nice to say here. Actually, the proof of the final paper on this conjecture was written here in one night. After a long time of discussion, of course, with collaborators. But I remember that it was nice to have the proof completed when the sun rises. That's a good memory. Okay. And when this result was done, I really thought, okay, what's next? I didn't have the impression there was something next, but in fact there is. Okay, so what's next? So let me mention only 2 directions, probably missing some. It's a good moment also to maybe apologize to a number of people I'm not quoting today because there are too many papers on the TOB theorems. I even saw on arXiv a paper posted 3 days ago, 150 pages long. Okay, so with the main topic being the TOB. So it's still an active topic of research and I'm forgetting people. Sorry. Okay, so 2 directions I want to mention. The functional analytic approach of square functions. So, and then the study of local TOB theorems for singular integrals and square function with LP testing conditions. So we have seen L infinity, L2, and LP has some motivations too. And I put singular integrals in red because in fact it's the proof show that it's much more difficult to control a singular integral by a TOB argument than a square function. Again, because you have to play with 2 kinds of constellation, one on the right, one on the left. When you have a square function, you only play with the constellation on the right, and the other one is already taken care of. Okay, so let me start with the functional analytic approach. Of course, this is, again, the ideas of Alan McIntosh that are very important here. So in a paper with Andreas Axelsson and Stephen Keefe, in fact, and the proof there was simplified later on, but they proved some kind, in the end, they proved some kind of estimate like this. So the square function, where, okay, d times b replaces, d times v times d times b replaces what was there before, divergence A grad. So here, this is a second order elliptic operator. And d, so if in order to have something that's second order here when you do the square, so d is a first order operator in the spatial variable. And then you have a b, which is a multiplication operator on some vector valued L2 space. So vector means for Cn, so it's a subspace of L2 valued in Cn, where n is some dimension or dimension plus 1 or whatever. And it has some accretivity that is, if you look at an operator on this subspace of this L2 space, then it has to be accretive, so bounded below basically. And D is a first order operator, so it's really a differential operator with constant coefficient. And then what is nice in this theory is that D has, we discovered, but it's not necessary, but at the time D was self-adjoint, and it was very useful in trying to prove this kind of inequality. So what they did in this paper, they tried to formulate a general criterion to prove that this inequality is true. So they didn't have exactly this operator. They had a different one. They turned out to be, what they did turned out to be equivalent to this kind of things. So what does that give, this inequality, in terms of the operator D times B? So it says that D times B has what is called the holomorphic functional calculus on this L2 space or subspace of L2 space. So this is a very important property because it allows you to take, for example, operators like the signum of D, of dB, or the characteristic function of the right half plane applied to dB, something like this, that you obtain by limiting arguments, but you know they are L2 bounded only if you know this property. And in fact, once you have proved this and chosen the proper D and proper B, then if you specialize with this choice, you see the Kato problem as an immediate corollary. So I'm not going to do it, but if you look at the paper here or this one, then you'll see it. You'll see this reduction. So the square function here is very central to proving, for example, the Kato square root problem. How much time do we have left? 20 minutes? Okay, good. Okay, yeah, maybe I'll give the debut later on. All right, so that was a very important step. The simplification also was oops, no, not this one. The simplification also was very important because it allowed to apply to many different things. So the application that Alan had in mind was towards geometry, when you had a manifold where the metric, you have L infinity perturbation of a metric, and you want to know whether some kind of estimates are stable in this perturbation. And this is a kind of estimate when you convert them into the geometric language that you need to conclude for this stability. And we'll see that this kind of simplified estimate I'm writing here has some other applications toward boundary value problems. So let's see that. Okay, so I was okay, yeah. So application. So I mentioned one that is not on this slide, but is towards geometry. Another one is this paper with Axelson and McIntosh, where we say that if you want to look at the boundary value problem on the upper half space, so the upper half space is, of course, yes, okay, X is on Rn. And so if you want to look at this kind of boundary value problem, you assume that the matrix coefficient do not depend on the transverse variable to the boundary here, which is Rn, if you want identified to Rn. Otherwise, you cannot hope to say anything on solving the Dirichlet problem. There are counterexamples. So you assume that in the first step that you do not have a dependence with respect to the transverse variable. And then you have a series of famous results, starting, of course, from Dalbeck's result for the Laplacian above Lipschitz graphs, but then Jerison-Koenig result when the A is real symmetric, and then Koenig-Pfeiffer for the Neumann and regularity problem. So we have obtained results on solvability of Dirichlet regularity Neumann problem. But in fact, so when I say there is a choice of D and B that allows to study boundary value problem for this elliptic equation, and the conclusion of this application is that you can not only reobtain those theorems in a different way, but you can extend them, get some others. You don't get the complete list of what's actually known, but you get a pretty long list. Another striking application is due to Andreas Rosen. So Andreas Rosen is Andreas Axelsson. Okay, he changed his name when he got married. That's something you can do easily in Sweden. Well, you can do it in other countries, but it's not as common. Okay. So he proved that for this particular dB, so the one that applies to this boundary value problem, having the functional calculus, the holomorphic functional calculus, it encodes things that are very important, which are the L2 boundedness of layer potentials. So you know when you want to solve an equation like this, what you try to do is you try to write down some Green's formula. And out of the Green's formula, you get that U of X is a sum of two guys. One is a representation by a single layer potential applied to the co-normal derivative. And the second guy is the double layer potential applied to the boundary data, U at the boundary. Okay, and so having these two operators in integral form, then you ask yourself, well, are they bounded in a natural way? So the double layer should be L2 bounded, and the single layer should be bounded from L2 to sub F H1, homogeneous H1. And it was actually a question for a long time. So, of course, specific results were known in the paper by Kaufman, McIntosh, Meyer. An application of what they did is the boundedness of the double layer potential above Lipschitz graphs, for example. Okay, but the thing here is that although so there is an algebraic correspondence, but in this kind of operator, the geometry is lost. There's nothing that you can, no geometric hints. So, but still, he was able to prove that, in fact, once you have an operator which we call the signum. So the signum, so dB has a spectrum in a double sector, like this, in a complex plane. Okay, so it has positive and negative spectrum in the sense of complex numbers, of course, and then you can compute an operator at the signum of dB. If you have this holomorphic functional calculus, it becomes an L2 bounded operator. And in the case where B is equal to the identity, what you would get is just in one dimension, you would get, for example, the diagonal matrix, the Hilbert transform as coefficients. Okay, so it's a generalization of the Hilbert transform, if you want. And having L2 boundedness, then you can ask yourself, okay, once we have this operator, where are the layer potential in these operators? And in fact, you can write this in some form where you see the double layer potential operator in one entry and the single layer operator in another entry. So in fact, the boundedness of this operator encodes these properties. So that's a very nice result. So of course, the L2 boundedness was nothing new because this was proved before. What was new is that the fact that he was able to identify these coefficients with the usual layer potential in the case where you can compute things with kernels. So that was a big result. And notice this is an a priori result. You don't need to know, you can solve Dirichlet or whatever Neumann problem to know that these layer potentials are bounded. So that's an a priori result for the boundary value problem. Okay, so that's two applications. Okay, let me just give you this slide 1, 2, 3, 4, 5, 7, just to tell you that the method of proofs there can be extended, so they are versatile in the sense that you can modify the method of proof to apply to some kind of different geometric settings or geometries. Okay, so Riemannian geometry, subelliptic operators, Riemannian manifolds on vector bundle, blah, blah, and Kato with mixed boundary condition, a little bit of publicity for Moritz, Segel, Allen, Mittelmann, and Torsdorf, because this is really solving the Lyon's problem, which is basically the Kato square root problem when you have a domain with mixed boundary conditions. So part of the domain you put Dirichlet condition, and on the other part you put the Neumann condition. And then you can play games and you look at degenerate elliptic operators when the degeneracy of the coefficient is controlled by A2 condition, so Mechanovtag 2, and then you can do boundary value problem for these kind of things, and I think the list is not closed. But okay, just to tell you this, you can adapt all these techniques, but basically it's not one theorem that you apply, you have to know the proof and modify the proof every time you want to apply it. Okay, that's how it is. Okay, another application which is very new is this a Parabolic Kato problem. So here you look at your favorite elliptic operator, but you had one variable, time, and you look at the parabolic operator with elliptic thing, which is this guy. But notice that here I allow the coefficient to depend on t. I didn't say how, but in a measurable way. And this is a big step. Now, there's basically no result known when you have a t-dependence that's measurable in this area. So actually, there's a big step in the next theorem compared to earlier results where you had time independence or some kind of time smoothness, like order 1/2 in time was basically at least necessary for all the other methods to apply in this kind of context. Okay, so the statement is that you replace your elliptic operator by a parabolic one, so you have two variables x and t, and then, well, first of all, it looks surprising, but it's a maximal accretive operator. If you don't know what it means, I'm not going to tell, but if you know, it means that there's some kind of boundness below of the operator, some kind of invertibility of the resolvent. But some kind of positivity also hidden somewhere. And then you can compute, once you have maximal accretive operator, you have a square root, and the square root has a domain that you expect from this inequality, which is basically the domain, the norm square of the form domain that you may want to associate to H. So what's a form domain for this operator? So for the elliptic part, this is what you do. You integrate A grad U grad V by doing integration by part. For d by dt, well, you consider d by dt as a square. The square of what? A square of half order derivatives, of course. What you compute by Fourier symbol. But of course, this is like a Fourier symbol, so this is basically you have I xi, then you have xi to the 1/2, then xi to the 1/2, which are the symbols, and then of course if you compute this, you don't have an equality, you need the signum. So therefore you need a Hilbert transform in the t variable. So you consider d by dt as a square with this formula. So of course that creates a difficulty, two difficulties. First of all, you get something that is not positive, of course. Well, you knew that from d by dt. And second of all, you get things that are non-local operators. But still, you can play this and try to see what you get as a form domain, and then try to see whether you can prove this. And in fact, it's true. So this is a generalization of the elliptic thing. But of course, you cannot take the elliptic result and just say, I'm going to generalize by adding a dummy variable, which is time. It doesn't work. But again, the strategy is the same. You have to create a first order operator dB in this context and prove some kind of square function estimate. There is a d missing, d lambda of a lambda, and prove a square function estimate here from 0 to infinity. Again, a T of B argument, but that's much more complicated than the elliptic one, in fact, because there you have new difficulties. First, the D that you create is no longer self-adjoint, and that's a big problem sometimes, and in the argument it's a problem. And the second thing is D contains half-order derivative in time, so therefore you have to expect non-local estimates. So let me just give you the D. So it's in some representation it's a 3 by 3 matrix. So you have this part, which is exactly the part that you deal with when you look at the elliptic theory, and then you have something added by the elliptic, by the parabolic component. So, and the D is like this. So it's a first order operator, of course, in the X variable, doesn't change, but it's a half order operator in the time variable. So that creates a lot of difficulty, in fact. And whenever you look at, when you want decay estimates, all the time you borderline in what you really need to do the harmonic analysis behind. Okay, so that's what I wanted to say. Okay, and the other thing is B, it works for dB here, so B is going to be a 3 by 3 matrix that is accretive. It's a multiplication operator, otherwise this kind of result don't work. But it cannot be an arbitrary B inside here. It has to be block diagonal in the sense that you get 0, zeros, something accretive here and something accretive there. Okay, so there's some structure that gives you some miracles in the computation, and then you can go on. So it's not a completely arbitrary argument here. It's tied to the specificity of these operators. While the elliptic guy, the dB could be arbitrarily anything when you work the estimate, because the D in the elliptic theory is always going to be local. Okay, and now to finish, in a few minutes, the second direction I was telling you, which is to look at local T of B theorem for with P testing conditions. So, okay, so the impetus was this paper by Steve, Camille Muscalo, Thierry Thiele, and I. It's actually a paper that followed the proof of the conjecture was in some of the arguments were inspired. I mean, this article contains different things as well, but okay, concerning the T of V part. So, and we worked in a model case where we replace the Kaldon-Zygmunt operators by something called perfect dyadic Kaldon-Zygmunt operator, which means that we have the same size estimate. And instead of having regularity condition, we have a little better than this. We have 0. 0, well, the kernel is constant on dyadic rectangles that do not touch the diagonal. So you take 2 dyadic intervals or dyadic cubes, okay, if you are in higher dimensions, and you take the product, and if the product doesn't contain the diagonal, you expect this kind of this relation. So it's, of course, it's very special. And this is the theorem that we obtained in this paper. So if you have a perfect Kaldon-Zygmunt operator. Okay, it was also a finite model, so in other words, the operator was a priori L2 bounded. There's no question of singularity here. It's just a matter of getting the bounds of the operator norm, depending on some conditions. Okay, suppose that for each dyadic cube, P, we can find functions, so B1P, B2P, supported on the dyadic cube, obeying this mean value condition, so this normalization here, and some L2 bounds. So on the same P, you have this L2 bounds for B1P, T, B1P square, and so on. And this is a natural normalization here. So in our terminology, they were called accretive systems, of course, adapted to T, because they are adapted because, in a sense, if you take any other function at random, you're likely not to check that this kind of function is defined and controlled. Okay, so but if you compare to Chris result, you have L2 condition. In Chris result, you had L infinity condition. Okay, so and then the strategy. Oh, there's a typo. The strategy, of course, if we follow Chris' argument, then we realize it doesn't work. So the strategy is different. Instead, we estimate T applied to the characteristic function of this same cube on L1, in L1 of this cube, and same thing for T star. And once we have estimate for this guy, we can apply a version of the T of 1 theorem, which is local. Okay, so it's a different strategy, but it does work, and it gives this kind of result. And in fact, the proof has some kind of miracles coming from the perfect theories that you can change the indexes here to arbitrary indices P, exponents for P and Q from 1 to infinity. And then at some point in the article we wrote this, so I quote, it's almost straightforward to generalize this result to Kaldon-Zygmunt operators, which has a kind of regularity condition we expect. And it's my fault if we wrote this, because this is not correct. But what's interesting, okay, it was not straightforward, but it gave some interesting series of papers later on. The problem here again is to control like what I call boundary integrals when you have two cubes or intervals that are very close to one another at different scales. So you are, at some point you have to control things like this or very similar things like this, and then you cannot do it. Except if maybe the exponents are in a good range where you can apply Holder's inequality. Okay, so the subdual range is when you can apply Holder, and when you cannot apply Holder, you don't know what to do. Okay, so an application, a motivation for looking at this for the true singular integrals was application to a single layer potential. And in fact, Steve Hoffman in his ICM address was stated this theorem. And in fact, it's not proved there. He has a proof somewhere on his webpage, but okay, you can find it. And the motivation for this was to prove the boundedness of the single layer potential for this operator on the upper aspect. But remember, I spoke of the Rosen's result. So at the time he was willing to do this, he didn't know. I mean, Rosen's result was not known. Okay, so still it was interesting to have this kind of boundedness result. And this is what we proved in this paper when you had real coefficient, but the proof depended on the fact that we knew the solvability of the Dirichlet problem. So we used that using the Poisson kernel, which is localized at some point here, at some pole, which is in a lower half space. Okay, so I'm not going to the motivation was an interesting statement at the time, but of course it's subsumed by Rosen's result, which does not use solvability of the Dirichlet problem whatsoever. So it's okay. But now there have been a series of results to try to understand where these P's and Q's could be improved to arbitrary P's and Q's for CZOs, not only perfect CZOs. So there was a series of results. So as I told you, with Young, we're able to treat the subdual case using an interesting idea, an algorithm of Belkin, Kaufman, and Rocklin, to show that, in fact, any Kaldron-Zygmunt operator, anyone, can be written as a sum of a perfect Kaldron-Zygmunt operator, so the one that I gave before, plus an error term that's always bounded. So whatsoever. So in fact, the boundedness of the CZO is equivalent to the boundedness of the perfect CZO you get in the sum. And okay, and then you think, okay, we do everything, all P's and Q's, but when you try to write down the passage from one to the other, you see that you need this condition. You cannot escape that. Okay, but then later on, we tried to remove that, so I did something with Routin, and then a different proof, and the interesting thing was some observation of Harding inequality on spaces of homogeneous type, which are no longer always true. So the Harding inequality is something that you integrate a function on a cube, and then another function on a cube of same size that is just nearby, and then you get the Holder estimate, and then you get a singular integral kernel between this function, and then you get what you would get by Holder's inequality. But it's not always true if you pick two balls in a space of homogeneous type that are very nearby and you do the same kind of thing. This inequality may not be true. So it was interesting to look at this. And okay, so there was some other works by Heaton and Nazaroff. They were able to almost prove this conjecture, where arbitrary P's and Q's, but in fact they had to enlarge a little bit the P as a cube here by a concentric 1 for some technical reasons, of course, but still the argument was very interesting. The idea, I didn't write the idea, okay. And then another one, Martican, Morglu, and Tolsa were able to obtain, to remove this buffer condition in some cases where the P's and Q's are subdual, which means this condition, so you cannot apply Holder. But they use that for antisymmetric kernels, they use this kind of estimate. And there is a range of exponent P's and Q's depending on some other exponents for which it works. So it's not always true. Another thing is that Heaton and Martikainen prove a version of Hoffman's real-only spaces of non-homogeneous type. Again, they use a random dyadic structures which they developed on these geometric doubling spaces. And I guess I'm finished. Another one is a series of papers by Lacy Kangas, say it right? Where they looked at perfect CZOs, but they get very nice new arguments, so improving what was done earlier. Okay, and the list is not finished, but I think I am finished.
Thank you. Are there any questions or comments? With a microphone.
Me.
So do you know about any possible applications of this improved TB theorem with these nice exponents?
Well, again, so when Steve formulated this conjecture for Kaldron-Zygmunt operator, he had an idea in mind of using some Poisson-type estimates for elliptic problems on domains where you have where you don't know that the boundary is rectifiable, and then he was expecting that the P you get is close to 1 and not above 2. So he really wanted to prove something like this of singular integral, but at some point he realized that he needed to do that not for the singular integral operator that was involved, but for a square function. And for a square function, it does work. So in fact, he's able to prove the thing that he wants for the square function, for the P close to 1, and then he has his application to his geometric problem. So, but again, for the general singular integral operator, no, I think it's a problem of just okay. Yeah, well, I mean, we all know that. I mean, trying to find another proof means that sometimes you can go forward and have another application. So I actually have an anecdote concerning this kind of question. When I was finishing my thesis, I gave a conference here in Marseille. It was not here. It was in, it was in the big building that's just across the street over there, because the audience was 150 people. So it was one of these meetings, first meetings on wavelet theory. So started by, and it was a very pluridisciplinary meeting where people coming from all sorts of science were there, like you have people in image theory, in signal theory, in biological science, studying chauve-souris, comment on dit ça? Bats, thank you. You had, of course, people from mathematics, you have theoretical physics, and so on. And then I was giving a short talk on my thesis. I was, a lot of math, not much of application. So it was another proof of Guy-Davis theorem on Barnesov-Cauchy integral on Kordak curves using wavelets. Okay. So it was another proof, and there was this woman whose name I don't remember, but doing image theory, asking out loud the question, so what's the point of reproving a theorem? I guess I have the answer today.
Are there any questions? Any further? No? If not, let's thank the speaker again.